Okay, so now we're going to review some concepts related to bond length, bond strength, and how things like resonance and bond order affect that. And we're going to introduce this concept of bond energy. So bond energy, okay, is the energy that's required. So we have to add energy in to break a bond. Okay, so remember that you need to add energy to break a bond. Okay, you don't get energy out of breaking bonds. You get energy out of making bonds. Okay, so how much energy are we talking about? Things like 150 to 950 kilojoules per mole of bonds that you're going to break. Okay, so single bonds are going to be your weakest kind of bond and have the lowest bond energy. So single bonds are going to be the weakest, and they're going to have the lowest bond energies. All right, so the example we have here is this bond right here, your bond between your oxygen and your hydrogen. I'm actually going to move that to the one that's actually broken in the figure. All right, and so when we break that bond, okay, we have to add in 463 kilojoules per mole. Okay, so we're going to add 463 kilojoules per mole of, this is the water molecules, so this is for a mole of water molecules. We would have to add that much amount of energy in to break that bond. Okay, so if we were, for example, trying to make hydrogen by the hydrolysis of water, by running an electric current through it, this is the amount of energy we'd have to do. Okay, now this is our bond energies. Okay, they're defined in the gas phase. Okay. And the reason that we kind of determine them, and again, these are things that are empirically determined, right? And so we do it in the gas phase so that we do not have to worry about the interaction between molecules, so that we're just looking at individual molecules and how much energy we have to put into them. Okay, so when we talk about breaking bonds, okay, and we say that you have to put energy in, that means your bond energy is positive. And it's always positive. Okay. And so that means you have to put energy into the system. If it were negative, for example, when you make bonds, that's always a negative bond energy because it releases energy. Okay. And so when something is positive, when we have to put energy into the system, okay, we call this an endothermic process. Endo means putting into, thermic means energy, right? So the term for when a system has to take in energy for a process to happen, we call that endothermic. Okay, so that's a little preview of what we call thermochemistry. Okay, so if we just look at, here are bond energies in the table here. Larger atoms are going to make weaker bonds. So let's look at these large atoms. So let's just compare something really big, sodium, and something much smaller, let's say boron. Okay, so if we take, let's look for atoms that are actually in our table. So, sorry. Let's look at and compare silicon to, so silicon's here, okay, and nitrogen, okay. So here's nitrogen. Nitrogen is much smaller, right? So nitrogen smaller than silicon. And if we look at, let's just look at a nitrogen hydrogen bond. Okay, so that would be 391 kilojoules per mole. That's our bond energy for that. And silicon bonded to hydrogen, that's 318 kilojoules per mole. Okay, so our larger atoms are going to give us weaker bonds. So the lower the bond energy, the weaker the bond. And think about, again, what bond energy means. Bond energy means how much energy I have to put in to break that bond. So if I have to put a larger number, a larger amount of energy in, that means that that connection between those two atoms is stronger. Okay. All right, so our second trend is that multiple bonds are stronger than single bonds, and we talked about this in class already. So if we just compare a carbon-carbon double bond with a carbon-carbon triple bond, you'll notice again that this is a bigger number, right? So larger bond enthalpy, stronger bond. All right. So if we had, say, what is good for carbon, okay, we see the same trend when we have nitrogen, right? A nitrogen-nitrogen double bond is weaker than a nitrogen-nitrogen triple bond. Now let's compare a nitrogen-nitrogen double bond with a nitrogen-oxygen double bond. Okay, this nitrogen-oxygen bond is stronger than the nitrogen-nitrogen bond. And if we go back here and look at our atom sizes, okay, oxygen is smaller than nitrogen. So when we add the smaller atom in, we get a stronger bond. Okay. All right. So bond order. Remember that this means single, double, or triple. Length and energy. So how do these, so we've talked about how bond energy and bond length on the previous slide are related. And all of those, again, are related to bond order. So if we just look at carbon, okay, and if we take a carbon-oxygen bond and we change that from being a single bond to a double bond to a triple bond. So our bond orders would be 1 here, 2 here, and 3 there. And as you'll notice, as you increase the bonds, the bond enthalpy increases, right? Now, if we were to measure the length of these, we would find that this is the shortest. And this is going to be the longest of the 3 bonds. Okay, so when we've been talking about bond energy, okay, the technical term for bond energy is bond dissociation enthalpy. Okay, so, and that is given the symbol delta H, where we're taking the enthalpy or the energy associated in the broken bond. So let's call that broken. Okay, and we're subtracting the energy in the molecule when the bond is intact. Okay. All right, so we talked about resonance in the peptide bond already, and here it is on another slide. So just to remind you, okay, when we have resonance, okay, our bond order is going to be in between the orders of the 2 resonance structures. So looking again at the peptide bond, so this is the bond that I drew on a previous slide in isolated format. Okay, here it is shown in the context of a full dipeptide, which is 2 amino acids connected. So this is 2 amino acids connected by a dipeptide, or by a peptide bond. What's called a peptide bond. And so I've circled the bond that is in question. And these are our 2 possible resonance structures, where one has a single bond between the carbon and the nitrogen and the other has a double bond. Okay, so in this case, again, the bond order of the peptide bond is what we would call 1.5. And we would, we could represent that by showing a dotted line as the second line between the carbon and the nitrogen that are there. All right, so bond order is really the number of bonding pairs divided by the number of bond locations. So in this example, okay, if I have 2 bonding pairs in one location, that's 2 bonds divided by 1 location. So that's my bond order. Okay, so to figure out the bond order for things with resonance, we would have my 2 electrons, and it would have or we'd have actually 3 bonding pairs, because 1, 2, and 3, and then we'd have some 2 different locations. All right, so in this case, that's how I get the 1.5. We've got 3 bond pairs divided by 2 possible locations. All right, so again, if we want to calculate our change in enthalpy, okay, we would consider the energy of the bond broken and the energy of the bonds formed. So breaking bonds requires energy. We call that endothermic, and your enthalpy value is positive. Okay, and so forming bonds is the opposite of that. It releases energy. We call that exothermic because energy exits the system, and your enthalpy is going to be negative in that case, because your system, your bond is, as you form the bond, energy is going to be lost. It's going to be released to the world. Okay, and remember, this is for gas phase things. This is valid for things in the gas phase. All right, so we can use bond energy, okay, to calculate the overall kind of energy of a reaction by looking at the energy of the bonds broken and the energy of the bonds that are formed. Okay, so if we look at this example here, let's look at what types of bonds are broken and which type of bonds are formed. Okay, so in this case, okay, we are breaking in order to make these compounds here, right? We are breaking this, and we're breaking this and this and this, okay? And we are making we're making 1, 2, 3, 4, 5, 6 NH bonds, okay? So 6 NH bonds made, okay? And then we have 1 N triple bond N broken, and 3 H bonds broken. All right, so the way we would do this is we would add up all the energies of the things that are broken, okay, and subtract the energy of the bonds that are made, okay. So let's add those up. So the bond energy for hydrogen-hydrogen is going to be 436. And we're going to multiply that by 3 because we've got 3 bonds. Okay. So that is accounting for our hydrogen. And this sigma here means we're summing things, we're adding them up. So we're going to add the energy of the nitrogen-nitrogen bond that has to break. So that's 945. Okay, so we're going to add all of that, and then what we're going to do is we're going to subtract the amount of energy of the bonds formed. Okay, and so we've got 6 times an NH bond is 391 kilojoules per mole. Right? All right, and so when we do that math out, that should come out to be the delta H of this chemical reaction is going to be, let's see, we got 436 times 3 plus 945, and we're going to subtract from that 6 times 391. And oops, I think I had a typo there. Times 6 minus plus times 3 plus, oops. Let me just check my math one last time. 436 times 3. 436 times 3 plus 945 minus 391 times 6. There we go. Minus 93. Minus 93 kilojoules per mole. All right. So what that tells us is it tells us that for this system, okay, if I mix these things together, okay, they are going to form 2 molecules of ammonia, and they're going to release this much energy here. All right. So the next thing that we're going to talk about is charge distribution in molecules, and I'm going to give you just a brief overview so that we can do some examples in class on Friday. Okay. All right. So if we are looking at bonds, okay, we've got a bond between 2 atoms. I'm just going to call them X and X. Okay. And so if they're the same atom, they're going to share electrons equally. If I have 2 different atoms, so let's say I have Y and X, okay, those 2 atoms have a different affinity for electrons, and so the electrons in this bond may be shared equally or maybe not. Maybe one of these atoms has a higher affinity for electrons, and we call that bond polarity. Okay, and so if we look at these 2 cases where we have 2 of the same atom and then 2 different atoms, okay, let's look at where the electrons are in their orbitals. So in this case, we have 2 of the same type, and this electron that's unpaired here is going to have the same energy as this electron that's not paired here. Okay. Now, when I look at carbon versus fluorine, you'll notice that the fluorine's 2p electron and the 2p electrons in the carbon are at different energies. Okay, so you'll notice that in carbon, all the orbitals are slightly higher in energy than fluorine. Remember, as you go to the right on the periodic table, your orbital energies decrease. So this diagram here is not me misaligning the orbital diagrams. They reflect the fact that these orbitals are higher in energy than these ones. Okay. So what happens, okay, is in this case, okay, the electrons that are going to be shared. So let's say, these are the electrons that are being shared in the bond. these electrons are going to be more attracted to the fluorine nucleus because they can get to a lower in energy place if they are shared and they share this orbital with this lower energy. Okay, so the electrons are more attracted to the fluorine because the 2p orbital in fluorine is lower in energy. So that's the real why of why an electron might be more attracted to one atom than another. And so what we'll talk about in class on Friday is something called electronegativity. So this is really going to be the kind of what is the phenomenon that we see. This is the why we see that phenomenon, and this is the what and how we use it practically. So that's it for this video.